Hi, we're Karen and Ed from the Stanford Autonomous Systems Lab, and we're here to present joint work with Vollprecht from ETH Zurich and our advisor, Professor Marco Pavone, on multimodal probabilistic model-based planning for human-robot interaction. In this paper, our primary case study is two-vehicle traffic weaving, a driving scenario where we assume that participants that start initially side by side must swap lanes in a limited time and distance as at a highway on-ramp and off-ramp. In order to learn interaction dynamics for traffic weaving, we started by collecting a dataset of a little over 1,000 traffic weaving trials between two humans on a driving simulator. We later used this simulator for human-in-the-loop testing against a robot agent taking the place of one of the human drivers.
Our methodology is to learn human action sequence distributions conditioned on interaction history and a candidate robot future trajectory. We use this predictive distribution for control in the context of model-based robot motion planning under uncertainty. It is critical that this distribution over human responses is multimodal. It is not clear who will pass whom in order to switch lanes. Correspondingly, there is a non-zero chance that a participant will accelerate or brake at any time during the interaction to achieve this separation. We feed a recurrent conditional variational autoencoder to our training data. This CVAE, for short, is a sequence-to-sequence model that produces a multimodal mixture distribution over human actions. Conditioned on the full interaction history, that is all states and controls of both participants leading up to the current time step, as well as conditioned on what the robot might plan to do over the prediction horizon. In our experiment, the horizon is 1.5 seconds.
Most of the action happens longitudinally, and we will briefly show a few examples of the prediction model in action, where the solid lines are the joint interaction history, the dashed blue line is the candidate robot future action, and the thin lines are sampled human responses colored by which mixture component of the distribution they were sampled from. Here we see that if the robot plans a hard acceleration, we generally predict, although not with 100% certainty, that the human is likely to decelerate in turn. Alternatively, starting from the same interaction history, if the robot plans a hard braking maneuver, we predict that the human is likely to accelerate to make the pass. If the robot considers a wait-and-see approach of maintaining speed, we see that our prediction model displays human modes of also maintaining speed, decelerating, or accelerating. We perform a parallel evaluation of 4,096 candidate robot action sequences, visualized here for a variety of initial robot states, sampling up to 1,000 human responses for the most promising candidates, and selecting the one with the lowest expected cost. We implement the first 0.3 seconds of this action sequence and replan in a receding horizon fashion.
We put our robot policy to the test, driving in simulation with humans in the loop. Our robot agent in white exhibits emergent behavior such as nudging in the hopes that the human driver will brake and give way. The bottom plot on the left shows a live visualization of predicted human longitudinal acceleration. Please come see our poster to discuss all the details we have left out.